All right, so now we're going to do some problems on Unit 1, Learning Target 4. So it's similar to Learning Target 3, except for now, before we can actually do the solving, we have to set up the equation ourselves from words. So we've got the population of Ohio was 7.8 million in 1995 and 11 million in the year 2005. Assume the population grows exponentially. Find the growth rate of the population. So the first thing, and I've already put it here because you'll be given it if it's on a test or quiz, is that the formula we're using is n of t equals n naught times e to the rt. Now keep in mind, this is just saying that n is a function of time. Population growth is a function of time. That's not n times t, that's function notation. Okay, remember, n of t is your ending population, what you end with. So if we look here, that's going to be 11 million. N naught is your starting population. So here that's going to be 7.8. Our rate is what we're looking for. We don't have that. That's what it's asking for in the question. And then our time, this kind of confuses some people. Our time is neither 1995 nor 2005. Our time is the amount of time that has passed. So from 1995 to 2005, that's 10 years. So T is 10. Okay, so now I just plug it in. So we're going to have 11 equals 7.8 e to the 10r. Right? I've just plugged it into our formula that we have here. This is an exponential equation. We need to use strategy 4. Right? We can't write e and 11 or 7.8, whatever it is, with the same base. So we're going to have to use strategy 4. But before we can use strategy 4, we need to be able to isolate the exponential. Because if we were to take the log right now, it wouldn't work. It wouldn't give us what we're looking for. So I'm going to divide both sides by 7.8 first. So we'll have 11 over 7.8 equals e to the 10r. Then what I'll do is I'll take the natural log of both sides. Okay, you don't have to use natural log here, but it is so incredibly easier to use natural log, and we'll see why in a second, because we've got natural log of 11 over 7.8. Well, now that this term has a log on it, we can use the power property to bring the exponent down. So we bring that exponent down, we've got 10r natural log of e, and here's where it becomes helpful, because if you remember, if you did not know, the natural log of e is really log base e of e, which is 1. So natural log of e, it goes away because multiplying by 1 doesn't do anything. It doesn't change anything. It doesn't affect it. So we can just get rid of it. So now we've got natural log of 11 over 7.8 equals 10r. We will divide both sides by 10 to isolate it, and then this is just something we type into our calculator. So we grab our calculator and we type natural log, let me grab my calculator, natural log of 11 divided by 7.8 divided by 10, and that gives us the rate, which is 0.034377. We look and see if it told us to round. It didn't, so I'm going to round to the nearest hundredth. I'm going to multiply by 100 first to turn it into a percentage. So it's going to be 3.43% is the population growth rate of Ohio. Okay, so I think the hardest part is maybe setting up the equation from the start. But once you have that, it's just using our strategy 4 to solve it out. Suppose JD's parents deposit $5,000 in a college fund that is compounded continuously when JD is 5 years old. If they would like to have $55,000 when JD graduates high school at 18, what interest rate would they need? So this is a problem where we are looking for the rate right? Similar to the last problem we did, we're still looking for the rate, but this is a money problem. And normally in the business world, they use this formula, A equals P to the ERT. You can see that that is super similar to this formula, right? This formula, the only thing that's different is these notations here for, starting and end amount. And we're going to be familiar with both of them. One of them seen in the science world, one of them seen in the business world. I want to expose you to both of them. So here, the cool thing is that makes this not too tricky is that, A still stands for the amount you have at the end. And in this case, they want to have $55,000. They want their account, to read $55,000 at the end of the time. The amount they're putting in is P, the principal, their investment, their deposit was $5,000. So they started with $5,000. Then the time, we've got from 5 years old to 18 years old. So how many years passed from 5 to 18? It's going to be 13 years. So they have 13 years schooling time for this to become enough money to go to college. And lastly, again, we're looking for the rate. The rate is the question mark here. So we can plug all of those into our equation, right? And even if you don't remember the difference between the two formulas, it's basically the same. It's end amount equals starting amount, E to the rate, which we don't have, times time, which is 13. Okay, and then from here, we solve this identically to how we've been solving these, how we solved the last one, right? We need to eventually get the variable out of the exponent, right? We can't solve with the variable up there, but we can't take any measures until we've isolated the exponential part. So I'm going to divide both sides by 5,000. We've got 55,000 divided by 5,000. Your zeros are going to cancel right off there, and we'll just be left with 55 over 5, which is 11. So we have 11 equals E to the 13R, right? At this point, we would then take the natural log of both sides. So natural log of 11 equals natural log of E to the 13R. And again, we do this, we do the log because it allows us to use the power property. We do natural log because it's log base E, and we've got an E here. So my exponent would come down. So I have natural log of 11 equals 13R natural log of E. And again, natural log of E is just 1. So it doesn't do much for us. It just goes away. We divide both sides by 13. And finally, we've got that our rate is going to be natural log of 11 divided by 13. And that's just something that we plug into our calculator. Natural log of 11 divided by 13 is 0.18445. Put it into a percentage by multiplying by 100 or moving the decimal place 2 places. We get that the rate needed is 18.45%. Okay, not likely that would happen. Not likely that you would find a bank willing to do that. So they're probably going to have to find another way to find JD some college money. Let's do one more word problem. Okay, we've got a radioactive element that decays at a rate of 3% continuously. There's 80 grams of the substance present, and we have 2 questions here. The first one is, how much of the substance remains after 20 years? And then the last one is, when will the amount of the substance drop below 50 grams? So we're going to start by just answering the first one. We know we're using N of t equals N naught to the ERT because this is a population problem. It's not anything to do financials. So let's fill in what we know for the first one. We know the time is 20 years, right? We are looking for the amount of decay after 20 years. We know we're starting with 80 grams. The rate is a 3% decay. So what we have to be careful with here is whenever we put it in a formula, we put it in as a decimal, but also since this is a decay, the rate is negative. So I have to make it negative 0.03. Okay, this is what I'm looking for. I'm looking for the amount I have after 10 or 20 years. So let's plug everything in. I don't know how much I have after 20 years. Remember, it's a function of time. I'm starting with 80. E to the rate is negative 0.03. The time is 20 years. Okay, and this is just a calculator problem. I don't have to use any algebra skills to simplify anything or solve for anything because my unknown is already on a side by itself, right? The unknown is already isolated. So I just type 80 e to the negative 0.6 into my calculator, and it tells me n of 20, the amount left after 20 years is 43.9 grams, right? It was 43.904, but we were asked to round to the nearest tenth, so that is what I did. So that is the answer to the first question. Okay, the second question wants to know when the amount of substance will drop below 50 grams. So now we don't have the time. Time is what we're looking for. That's our unknown, and the amount we're going to end up with is 50 grams. So using a little bit of logic here to kind of check ourselves and make sure our answer is okay, if after 20 years we have 43.9 grams left, well then it makes sense that it's going to take less than 20 years till we have 50 grams left. So it's always important when you're working on a problem in the context of a word problem to look at your answer in that context. Does my answer make sense, or did I potentially make an algebra error? So here the setup's going to be 50 grams equals 80 grams e to the rate is still, negative 0.03. It's the time that we don't know. Okay, we don't know how long that's going to take. But now we've got our variable in the exponent. We have to solve for that. We can't just type this into our calculator because we haven't isolated the variable yet. So the first thing I'm going to do is divide both sides by 80 to isolate that exponential part. That's going to leave me with 5/8 equals e to the negative 0.03 t. Then I'm going to go ahead, take the natural log of both sides, because that sets me up to be able to use the power property and bring down my exponent. So now I've got natural log of 5/8 equals negative 0.03 t, natural log of e. Again, natural log of e equals 1. That's the whole reason we used natural log rather than log. So that goes away. Then I divide both sides by negative 0.03, divide by negative 0.03, and into my calculator I type natural log of 5 divided by 8 over negative 0.03, and that will give me t, which let's see what that is. Natural log 5 divided by 8, close parentheses, divided by negative 0.03. I got 15.5 or 15.66678 years. We'll round to, I don't know, the nearest hundredth, we'll say. So the time is 15.67 years. And we're done.